Hello AP Chemers, hope you're doing well. Today we're going to talk about something called hydrolysis. So usually we know how to distinguish between acids and bases. Acids typically are substances that start with an H. Bases are things that typically end with hydroxide or common bases that we know of like ammonia, like baking soda, like things that have, a nitrogen with a lone pair on it, amines and such. And so we know that acids have a pH lower than 7, bases have a pH higher than 7, and we think of other substances as neutral, like salts, for example, ionic compounds, like NaCl or CaCl2 or something like that. We think of those as neutral. Well, that's not exactly true. Some salts are neutral, but other salts are just a tiny bit acidic or just a tiny bit basic, either slightly acidic or slightly basic. And so let's look at some examples of those. Well, if you have an anion of a weak acid, that ends up being a very, very weak base. What does an anion of a weak acid mean? An example of a weak acid, for example, is HCN. HCN is a weak acid, so the anion of that is Cn minus. If you have a salt that has Cn minus, that actually turns out to be slightly basic. And that's what it means by anions of weak acids can act as bases. So for example, if I have NaCN, that's a salt, an ionic substance. It is completely soluble because it has some sodium ions in it. And so that will 100% dissociate into Na plus and Cn minuses. But then those Cn minuses can undergo hydrolysis. What that means is they can react with water, and when it reacts with water, it grabs an H plus from the water to form HCN, and then what's left is OH minus. And so because this reaction produces OH minuses, that means your hydroxide to H plus ions are not going to be equal, and you're going to have more hydroxides, which means it's going to be a basic solution. Now, similarly, cations of weak bases can act as weak acids. Well, what does that mean? For example, ammonia, NH3, if you put that in water, aqueous ammonia is the same thing as ammonium hydroxide, NH4OH. So, NH3 and water is the same thing as NH4OH. That's just what this is aqueous ammonia. So anyway, we know that ammonia is a weak base. The cation of that is ammonium ion. And so if you have a salt that has ammonium ion, if you have an ionic substance that has ammonium ion in it, then that can act as an acid. So for example, let's say I have some ammonium chloride right here, and I'm going to dissolve that, so that will dissolve completely. NH4 plus and Cl minus would be the dissociated ions. But then the NH4 plus could undergo hydrolysis. It could give off an H plus to the water, and so you'd end up with ammonia and then some H pluses. Remember, hydroniums are the same thing as H pluses. And so now you have extra H pluses, and so that makes the solution slightly acidic. So hydrolysis itself is a reaction in water of weak acid anions and weak base cations. Let's write that down. A reaction in water of weak acid anions. Oh, my stylus is acting up again. There we go. Alright, now it turns out that if you have an ion coming from a strong acid or a strong base, those do not undergo hydrolysis. But if they come from weak acids or weak bases, then they can undergo hydrolysis. For example, here the Na plus is a cation of a strong base, like NaOH is a strong base, so that's a cation of a strong base. That would not undergo hydrolysis. But Cn minus, because it's from a weak acid like HCN, that would undergo hydrolysis. Same thing here. The NH4 plus is from ammonium hydroxide, which is a weak base, so that would undergo hydrolysis. Cl minus is the anion of a strong acid, HCl, that would not undergo hydrolysis. So things that come from strong acids or strong bases would not undergo hydrolysis. Things that come from weak acids or weak bases would undergo hydrolysis. So weak is the key word here. All right, let's try a problem. So let's say I have 0.01 moles of sodium acetate, and it's added to water to make a 1 liter solution. What would the pH be? So the first thing you would do is you would start out by writing your dissociation equation of your salt, because this is a salt here. So Na. Okay, so NaCH3COO, sodium acetate, would dissociate completely, because it's a soluble salt, into Na plus and CH3COO minus. That's one arrow. Now, the Na plus is a cation of a strong base, so that would not do anything. But the acetate is the anion of a weak acid, like acetic acid is weak, and so that could undergo hydrolysis. So then your next step would be to write your hydrolysis equation. So what you do is you write out your ion, so CH3COO minus, and you add water to that, and then it's in equilibrium, so 2 arrows. In this case, the acetate ion will grab an H plus from the water to form that weak acid, which is acetic acid, and you can write the H in front or at the end. I prefer to write at the end, so CH3 COOH. I put my H here, but you could always put it there. That doesn't matter. And then since the water gave off an H plus to make the acetic acid, then what's left of the water is a hydroxide ion. So guess what type of solution that is? That's going to be a basic solution. Now if you wanted the pH, then you would want to do an ice chart, just like any weak acid or weak base. You would always do an ice chart since there's an equilibrium. So I'm going to write ice. And initially I have 0.01 moles of the sodium acetate in 1 liter, and so this is 0.01 molar. So this is also 0.01 molar, and this is also 0.01 molar. And so my acetate to start with is 0.01 molar. I don't care about the water because it's a liquid. This is 0 and 0 to start with. Minus x plus x plus x. So this is 0.01 minus x, x, and x. And now I'll set up my K expression in this case because I know that this is a base. That tells me that I use Kb. So I'm going to use my Kb expression. So the Kb is going to be the concentration of the CH3COOH times the hydroxide ion concentration over the acetate ion concentration. And I would look up the Kb for my acetate ion. So that ends up being 5.6 times 10 to the negative 10th is equal to x times x over 0.01 minus x. When you solve for that, you will get that x which is the hydroxide ion concentration, ends up being 2.36 times 10 to the negative 6 molar. And that's a 3 there, I'm sorry. And so the pH is negative, sorry, the POH, since this is the hydroxide ion concentration, you have to find the POH first. POH would be negative log of that, which is 5.63. And so the pH is 14 minus that, which ends up being 8.37. So indeed, it is a little bit basic. So how do you know if a salt is acidic, basic, or neutral? So what you do is you look at the ions that make up that salt and you decide, are they ions of strong acids or bases, or are they ions of weak acids and bases? So let's start with, let's say your ions are of strong acids or strong bases. Let's list those real quick so that you have them in your notes. So ions of strong acids would be Cl minus, Br minus, I minus, ClO4 minus, NO3 minus, and HSO4 minus. Now I'm going to underline this one, put a little question mark there. Let's talk about that one for a second. So the reason why the ions of strong acids or strong bases would not undergo hydrolysis is because if you were to form a strong acid or a strong base, so for example, Cl minus, if it reacts with water, grabs NH from it to form HCl, that's never going to happen because once you form HCl, it's going to dissociate back into the ions H plus and Cl minus. It will never lie towards the side of a strong acid or a strong base because by definition, a strong acid or a strong base will immediately dissociate. And so you will never form any of these strong acids. So none of these ions combine with H plus. You'll never form HCl, HBr, HI, HClO4, HNO3 minus. Sorry, HNO3, not without the minus. Now, with HSO4 minus, that is the ion of a strong acid. So it will never combine with an H plus to form H2SO4 because that's a strong acid. However, because this has an H in it, there's no reason why that would not undergo hydrolysis to give off an H plus to form SO4 2 minus. So it could undergo hydrolysis the other way by actually giving off an H plus as opposed to gaining an H plus. So that one's a little bit iffy. When you see it, you don't say that it's neutral. You kind of have to investigate a little more. All right, how about strong bases? So the ions of strong bases, remember strong bases are group 1 hydroxides and then calcium, strontium, and barium hydroxides. So the ions there that you would see would be Na plus, Li plus, K plus, Rb plus, I guess you could think of francium and cesium. And again, I'm sorry, my stylus is not working. That's a cesium there, Cs plus. So that's group 1. And then you also have strontium, barium, and also calcium. So let's say you have a salt that is sodium nitrate. So you see, well, Na plus is an ion of a strong base. That does not undergo hydrolysis. NO3 minus, ion of a strong acid. That does not undergo hydrolysis. Since neither undergoes hydrolysis, the pH would remain at 7. Same thing with KCl, same thing with CaBr2. So those would be neutral salts. Let's say you have a salt where the weak acid So one of the ions comes from a weak acid, but the other ion is from a strong base. For example, let's say NaF. So NaF would dissociate 100% into Na plus and F minus. Then you'd look at those ions and say, well, Na plus comes from a strong base, so that would not undergo hydrolysis. F minus comes from a weak acid, so that can undergo hydrolysis. So then you write your hydrolysis equation, and you say F minus can react with water, and that would be an equilibrium. The F minus can grab an H plus from the water to form HF, and then the water would be left with OH minus, and so that's going to be a basic solution. All right, what if you have the opposite? So what if the cation is from a weak base, but the anion is from a strong acid? An example of that, for example, would be NH4I. So let's say you have NH4I that 100% dissociates into NH4 plus and I minus. Now, the I minus comes from HI, which is a strong acid, but the NH4 plus is an ion of a weak base, so that could undergo hydrolysis. So then you write out your hydrolysis equation. So you have NH4 plus H2O. That's going to be an equilibrium. That's H2O there. So the NH4 plus can give off NH plus to form NH3. And then you'd also have hydronium ion, since that oxygen gained NH plus from the ammonia. So that, because it has H3O pluses, would be slightly acidic. Now, 1 through 3 here, those are really important for the AP exam. Number 4, I highly doubt would be on the AP exam because complex ions are out of the AP exam. But what that's saying is if you have salts of highly charged metal ions, those would be acidic. And so the examples that we have here are listed. These metals have a high charge. And so what happens is when you put those in water, they grab a bunch of waters and those waters get into their crystals. You can see here that they form complex ions. They are ions with water in them. And then that complex ion gives off an H plus. And so those produce acidic solutions. For the AP exam, you will not be responsible for knowing how to do this. You need to know it for my test, but then you don't need to know it to review for your final or your AP exam. So let's try that here. Let's say you have some aluminum chloride right here, and we have 0.01 molar of it, and we want to know what the pH of that solution is. So what happens is when you put aluminum chloride in water, so let's say you have AlCl3, that completely dissociates into Al3 plus and then 3Cl minus. Now, the Cl minus is the ion of a strong acid, so that would not undergo hydrolysis, but the Al3 plus could. So what happens then is that the Al3 plus combines with 6 waters to form a complex ion, which is Al with 6 waters, and then that 3 plus is still there because we're just adding neutral water to it. It's getting in the crystal. Then that complex ion, the Al H2O 6 3 plus, then has an equilibrium where it produces an H plus from one of those waters. And then what's left, this is a little bit confusing, So this had 6 waters in it. One of the waters gave off an H+. So now that aluminum has only 5 waters, because that 6th water broke up, right? So it only has 5 waters now. That 6th water gave off an H+, and what's left of it is an OH-. Now OH- combined with that 3+ charge forms 2+. Again, you only need to know this for my test. So for all of these, they're going to be exactly the same way, except, you know, instead of aluminum, it could be a different metal. That charge could slightly be different. So if I wanted to get the pH for that, what you would do is you would do an ice chart. And here you have 0.01 molar, 0 and 0, plus X. I'm sorry, this is minus X. Plus X. Plus X. So you have X, X, and then 0.01 minus X. You would have to be given the Ka for this, and it's Ka because this is acidic. The Ka values are given to us right here. If we're looking for aluminum, the complex ion for it has a 7.9 times 10 to negative 6 Ka. So your Ka is going to be equal to the concentration of the H+ times the concentration of this over the concentration of your original complex ion. So here's the work for it. So 7.9 times 10 to the negative 6 equals X times X over 0.01 minus X. If you solve for X, in this case, you would get 2.7 times 10 to the negative 4th, which is your H+ concentration. That says 2.7 times 10 to the negative 4th molar. And if you want the pH, it would be negative log of that, which ends up being 3.56. Alright. Now, I didn't leave myself much room. Again, I'm sorry, my stylus is giving me a hard time here, so I'm having a hard time writing. But after we found the pH, now we also want to find the Kb. And so to do that, just like with any acid and its conjugate or with any base and its conjugate, remember Ka times Kb is equal to Kw. So I'll find a spot to write that. I just went ahead and erased part of this so I can have some room here. So Ka times Kb for any acid and its conjugate base is equal to Kw, which is the dissociation of water. So if you're solving for Kb, it's going to be Kw, which is 1.0 times 10 to the negative 14. Over Ka, which is in this case is 7.9 times 10 to the negative 6. Kb in this case ends up being 1.3 times 10 to the negative 9th. All right, the next table in our notes just basically lists what we just talked about earlier in that page, just in a table format so it's easy to read. So let's go through it together. So let's say you have a salt where the cation is from a strong base and the anion is from a strong acid. Like, for example, NaCl. Na plus is the ion of NaOH, which is a strong base. Cl minus is the anion of HCl, which is a strong acid. So since they both come from strong acids and bases, then you cannot undergo hydrolysis for either one of them, and so your pH remains at 7, which would be neutral. Next, let's say that your cation is from a strong base, but your anion is from weak acid. For example, let's look at KNO2. So KNO2, K plus comes from KOH, which is strong. So we're going to ignore that. That does not undergo hydrolysis. NO2 minus comes from HNO2, which is weak. And so that would undergo hydrolysis. The anion would. So NO2 minus would grab an H plus from the water, producing OH minuses and HNO2. And so since it's producing OH minuses, that means it's going to be basic. Your pH will be higher than 7. So it'll be basic. What if you have the other scenario, the opposite? So the cation is from a weak base, but the anion is from a strong acid. For example, NH4Cl. So NH4 plus is from a weak base, so that could undergo hydrolysis. Cl minus is from a strong acid, so that would not undergo hydrolysis. So NH4 plus can, if you react that with water, it gives off H plus for the water, and so you form ammonia and H3O plus or H plus, which is makes it more acidic, and so your pH is less than 7. We're going to skip this one and we'll come back to it. Let's go to the last one here. If you have a small highly charged cation and then the anion is from a strong acid, like for example what we talked about with AlCl3, so Cl minuses would not undergo hydrolysis because they come from HCl, which is strong, but the Al3 plus can, it forms this complex ion and then it gives off an H plus, so that's going to also be acidic and the pH will be lower than 7. Now, what if both your cation and your anion are from weak acids and bases? Like, for example, NH4NO2. The NH4 plus can undergo hydrolysis, giving off H pluses, so it's going to be acidic. The NO2 minuses can react with water, grabbing an H plus from it to form HNO2 and OH minuses, which is going to be basic. So what is the solution going to be? Well, it depends. In this case, you would look up the Ka and the Kb values. You'd look up the Ka for the acidic portion, which is the NH4 plus. You look up the Kb for the basic portion, which is the NO2 minus, and you compare the two. If Ka is larger, then that means the acid wins. It's going to be acidic, less than 7. If Kb is larger, that means the base wins, and the pH will be higher than 7. It's going to be basic. If Ka and Kb are pretty much the same number, then it's going to be neutral. And that happens actually with ammonium acetate. It turns out that NH4 plus, the Ka for that, and the Kb for the acetate ion are both 5.6 times 10 to the negative 10th. That's a coincidence, but it happens, and so in that case, that would be neutral. So that's what this is saying right here. If K is larger, then it's going to be acidic. If Kb is larger, then it's going to be basic. If both of them are equal to each other, then it's going to be neutral. Let's try a couple of examples. So we want to predict the pH of each of the aqueous solutions, whether they're going to be greater than, equal to, or less than 7. Let's start with NaCl. So what you do is you look at the ions that it's made up of. So Na plus, that comes from a strong base, so that would not undergo hydrolysis. Cl minus comes from HCl, which is a strong acid that does not undergo hydrolysis. Neither one undergoes hydrolysis, so that would be pH equal to 7. It's going to be neutral. Okay, next we're going to look at FeCl3. So the Cl minuses in FeCl3 come from strong acids, so those would not undergo hydrolysis, but the Fe3 plus can. And remember, that's a small, highly charged metal cation, and so that forms a complex ion, gives off H pluses, and so that is going to be acidic with a pH that is less than 7. Let's look at the next one. We have NH4NO3. So with NH4NO3, the nitrates, NO3 minuses, come from strong acids, so those would not undergo hydrolysis. But the NH4 plus comes from a weak base, and so that could undergo hydrolysis. Remember, the NH4 plus reacts with water, you form ammonia and H pluses, and so that's also going to be acidic, and the pH would be less than 7 as well. Let's look at D, NaHCO3. Excuse me. So Na plus comes from a strong base that would not undergo hydrolysis, but the HCO3 minus can. Now let's look at that one a little bit closer. HCO3 minus, I'm going to write the equations. So HCO3 minus can actually do two things. It could grab an H plus from the water to form H2CO3, and then you'd have OH minuses, so that would be basic. Or it has an H in it. It could give off an H plus to form CO3 2 minus, and then H3O plus, which would make it acidic. So which one is it? Well, if it could do both, which means if it's an anion that has a hydrogen in it, it could do both, then what you do is you look up the Ka and the Kb. So if you look at the table in your notes, you will see that the Ka is 4.8 times 10 to the negative 11. The Kb is actually 2.4 times 10 to the negative 8. Kb is much higher, which tells you that it's going to be basic, so this is the reaction that is likely to occur. Now, hopefully that makes sense to you because this is sodium bicarbonate, and we know that that's basic. You've all added vinegar to it or HCl or something to it, and it bubbles up, gives off carbon dioxide from the H2CO3 there decomposing. Anyway, you know that baking soda is basic, and so hopefully you check your answers and make sure that they do make sense. If it was a substance that you don't know, then you do what we just did where you compare the Ka and the Kb and see which one is larger. All right, one more question. Let's say that I have the following substances, and I want to rank them from lowest to highest pH, or from most basic, or sorry, from most acidic to most basic. How would you do that? Well, here's a guide for you. So, on one extreme you have acidic substances, on the other extreme you have basic substances, and then in the middle are neutral. So, acidic substances, and this works best if you're comparing concentration. pH is reliant on the concentration of your acid and base, and then also the strength, how much it dissociates. So the pH actually relies on both things. So let's say that they're all, 10th molar solutions. So the most acidic, which is the lowest pH, is going to be the strong acid. Following that would be a weak acid. So your acids are obviously more acidic. Then, on the other extreme, for your bases, the most basic is going to be the strong base, followed by a weak base. And then in the middle are all your salts. And then your salts could be neutral, slightly acidic, or slightly basic. So any acid, whether strong or weak, is going to be more acidic than a salt. Any base, whether strong or weak, is going to be more basic than a salt. So let's try to rank these here. So if we're going in order of increasing pH, that means from lowest pH, which is most acidic. And so you're going to start with your strong acids. And so let's skim through here. Do we have any strong acids? Yep, HClO4. So that's going to be my number 1. All right. Do we have any more strong acids? No, we don't. So now let's move on to weak acids. Do we have any weak acids? Yep, we do. H2SO3 is a weak acid. All right, next, since we don't have any other acids, weak or strong, now we're going to go to the salts. Let's see if we can find any acidic salts. So acidic salts are going to be salts where your cation comes from a weak base. So let's skim through those. And it looks like NH4NO3. That one, the NO3 minus would not undergo hydrolysis, but the NH4 plus can, and that gives off H pluses. Okay, any more acidic salts? Doesn't look like it. So now neutral salts. Do we have any neutral salts? Those would be the ones where both the cation and the anion come from strong acids and bases, so no hydrolysis. And so LiF would fit that. I'm sorry, not LiF, KS. Ooh. I apologize. That should not say LiF. That should say LiBr there. I apologize. That's how the question was supposed to be. I'm sorry about that. So if it was LiBr, that would be a neutral salt. So that would be number 4. And then that looks like it's it for neutral salts. So now let's go to the basic stuff. So the least basic would be a basic salt. And so KSCN would be a basic salt. The K plus does not undergo hydrolysis, but the CN minus can undergo hydrolysis. So that would be our number 5. That's it for all the salts. So now we can go to the bases. And so the base with the lowest pH, or the least basic, would be a weak base. And so that would be the aluminum hydroxide there. That's number 6. And then finally a strong base, so that would be number 7. All right, that takes care of salts and their acidity and basicity. Have a great and wonderful day.